So thank you. It's a pleasure to be here. I'm going to talk about AI. I will start with describing you some of my personal experience from around 2000 until today, working in several companies and universities around AI. And what is astonishing about AI is the pace of changes that happen. We see technologies, we see revolutions, and I'm going to focus on 4 revolutions that happened in the last 4 years, some of them in the last year. So it's really amazing. It's not something that you see in every field, in every scientific field. And it makes us also think about safety of AI, and should we be alarmed about this space and the change that happens in this field. So as I said, I will start off talking about 6 AI revolutions: the machine learning revolution, deep learning, self-supervised foundation models, consolidation, Sim2Real, and reasoning. So the last 4 happened in the last 4 years. And let's go over them and see what does it mean. So again, a personal perspective. In 2000, I was a young student working in some startup company, trying to detect the circumference of heads of fetus in order to know how to do the delivery. So the methods that we used were classical AI. There was no machine learning. There was no deep learning. We just wrote algorithms that try to find ellipses in images, noisy images like ultrasound images. This is 2000. Then I finished my master's degree. I finished my PhD. I was in Chicago at Toyota Technological Institute for 2 years. I came back to Jerusalem as a faculty. And I've joined Mobileye as a consultant in 2010. And in 10 years, the technology of how you detect things in images was drastically different. In 2010, say we want to detect a traffic light, like you see here on the top of the image. So you do not write code that try to find rectangles, but instead you define general features. These features are hand-tuned, and then you apply machine learning methods like support vector machines and AdaBoost. These machine learning techniques were very popular. From 2000 to 2010, there were the dominating approaches for tasks in computer vision. So what is machine learning? Very briefly, it's a center of AI and data science. I guess that everybody knows, but by and large, instead of telling the computer what you want it to do, you just collect a bunch of examples. So images, and manually you label rectangles of traffic lights in the image, and you let the computer, with techniques of machine learning, figure out by itself a rule that takes a new image and found all the traffic lights in the image. Okay, so instead of writing the rule, you just show examples. Here is example 1, 2, 3, and let the computer figure out itself, the algorithm figure out itself what to do. So this was a revolution in the perspective of industry. It took about 10 years from having a manual expert that write software for computer vision to everybody is using machine learning. Right. But then 2012, 2 years later, came the seminal paper of Krzyzewski, Sutskever, and Hinton about solving ImageNet using deep neural network, deep convolutional neural networks. So instead of hand-tuned features and then applying SVM or AdaBoost on top of it, you are now just feeding the computer the raw images and letting it learn everything by itself. So you give an image, you give the labels. All the rest is done by the machine. The machine learns by itself from the image up to the output that you want. And when I saw this paper, I discussed with Amnon Shashua about the implications to Mobileye, and we decided to push it forward fast. And we implemented deep learning. I myself wrote a package for doing deep learning. This was before TensorFlow and before all the packages that we have today. And we applied it to Mobileye chip, which is called IQ. And this was a basic technology behind Tesla Autopilot Gen 1 in 2014. And to the best of my knowledge, this was the first time in the world that a deep learning-based technology was applied on an embedded system. So this is deep learning. And from then, from around 2012, deep learning there was 1 year that were 10% of the papers in computer vision conferences using deep learning, and the year after that, 90% of the papers used deep learning. So this was really a revolution, and during the times in the decade from 2010 to 2020, supervised deep learning became a very successful method whenever a company could invest in generating high-quality labels, and you wanted to solve a specific problem. So as an example, take Mobileye. You want to detect cars in an image, pedestrian, traffic lights, etc. So we invested in having people manually labeling a lot of images for cars, for pedestrians, for traffic lights. And we wanted to solve these specific problems, and deep learning was the best solution for this task. Then in 2019, I joined a startup calling AI21 Labs, working on rephrasing problems. So you can see up here, the product is called WordTune, and you see a sentence. This opportunity interests me, and the system should suggest you rephrasing of this sentence. So if we think about solving this problem using supervised deep learning, it is very complicated, because letting humans come up with many options for rephrasing a sentence is a difficult task. There is no really a clear definition of what is a good rephrasing of a sentence. It's subjective, and there are more than one possible answer, and writing rephrasing is a long task for humans. So then came another revolution, a new technology, which is called self-supervised foundation models. So in self-supervised foundation models, there are no labels. We do not tell the computer what we want to do. We use the input itself as fake labels. I will elaborate on it in a minute. And so we are not solving any specific task, okay? But then at the end of the day, we do want to solve some specific task. So what we're doing is something that is called in-context learning. So the foundation models is learned for a generic task, for a generic fake task. And then when you are approaching a specific task like rephrasing, then you just explain the model that you would now want it to be specifically applied to this specific task. And then the model by itself in the context learn that this is what you want to do and solve it. So let me elaborate how it works. There is a pre-training phase. In text, very easy to explain, we have a bunch of text which we tokenize. So we have a list of tokens, T1, T2, Tn, okay? Think about a token as word, even though it's not necessarily a word. It can be part of a word, but let's think about it as a word, okay? And then you learn a neural network that minimizes minus the log of the probability of Ti given the prefix Ti minus 1 to T1, okay? So I am going to, what's coming next? So we are asking the question, what's coming next? Of course, I'm going to tell you, I'm going to go away. There are many possibilities, but there is a probability over what comes next. And the goal of the network is to learn the probability of what's coming next. And we call it self-supervised because we give it the actual answer of what comes next as a fake label. This what comes next is what's actually written in the text. So we use the text itself as labeling itself. This is why we call it self-supervised. It is a task-agnostic method of learning. We didn't tell the model that we wanted to do rephrasing or we wanted to support chat or search or whatever, what we are doing later with the model. It's a foundation model, which is learned just by self-supervision. OK, so we have this foundation model. Now what? Now we have a specific task that we want to solve. Then we perform something that is called in-context learning. The model is trained to be a good model of the internet, just what comes next in the internet, because we're training it on massive scale internet data. And then by telling it in the prompt in the beginning, we are telling it what exactly we want to do. And there are several ways to do it. For example, zero shot. We just, the example here, we just show in the prompt, translate English to French, cheese, and then the model needs to complete what comes next. So once we phrase it like this and the model learn to predict the next word, it is likely that it will predict the next, the translation of English to French. So we have a task description, translate English to French, and a beginning of a question. And then the model needs to explain, to predict what's coming next. But we can do more. We can have one shot, meaning that we are giving complete one example. So translate English to French, and we add sea otter, Luther de mer, and then cheese, and then the model see one example of what we want to achieve, or few shot, which is several examples of what we want to achieve. So this is from 2020, okay? We're talking about 2-3 years ago, okay? And this is really amazing to take something that was trained just to be a good model of the internet to show the model a prompt of what a specific problem we want to achieve, and the model simply solves many of these problems. Okay. But this is not the end of the revolutions. So there is also the consolidation revolution. So when I was doing my PhD studies, there were experts in computer vision, speech recognition, different community, natural language processing, a different community, etc. There were many, many communities. I was not belonging to any of these communities. I was in the machine learning communities. Today, I'm working on computer vision problems at Mobileye, speech processing problems at OrCam, natural language processing at AI21. I'm not an expert in any of these fields. The reason I can do it is because all of these fields went through a consolidation of techniques. So all of these fields relying on deep learning, okay? And moreover, in recent years, there is also a consolidation of the architecture. So you could have said that, okay, there is deep learning for speech processing and deep learning from computer vision. The architecture are different, and this distinguishes between an expert in computer vision and an expert in speech processing. No more. Today, even the architectures of the neural networks are almost the same in all of these fields. Yeah, there are little things that are different here and there, but by and large, if you know to do computer vision, you know how to do speech processing or natural language processing, which is really amazing. Again, if you look 15 years back, this was not the case. People from computer vision and NLP didn't even know to speak to each other effectively and exchange ideas. Today, you know, they are all talking about transformers and everyone understands everything. So this is a consolidation revolution. Okay, so far we talked about technologies that falls into what I call the learning paradigm of learning from data. So if we want to solve a computer vision task, we want to look at many, many images, okay, maybe with labels, and we learn from the data itself, okay? We are passive. We are not affecting anything. We are just look at images and understand what is an image and what is in an image by looking, by observing the images, by learning from the data. But sometimes you cannot just learn by look at someone else. If you want to do gymnastics, okay, you can, or if you want to be a good basketball player, okay, you can watch Maccabi or NBA, whatever you prefer, or Apoel, I don't know. You can watch the TV. It will not make you a very good basketball player, right? You need to practice. You need to experience it yourself. So the second paradigm of learning is learning from experience, not from data, but from experience. You want actually to try things out until you figure it out, okay? So if you want to build a robot, okay, and you want it to know how to walk, you need that the robot will practice walking, okay? If you want the robot to grab something, you need it to practice grabbing. So how we do it, how we learn from experience. So one option is just let the robot experience in the real world, okay? So put the robot here and let him learn how to walk. The problem with this is that it is slow because we are limited by physics. The time is progressing at a certain pace, and it is dangerous, okay? So the robot can fail, or if it is an autonomous car, then it can hit someone, right? So we don't want to practice in the real world, okay? A much better approach is to practice in the simulated world. So we can simulate the real world and let the robot or the car practice in the simulated world. We can do it very, very fast because we have many computers. We can simulate in parallel on many, many computers. We can simulate faster than real time, okay? So we can be much faster in our learning abilities. But the problem, and it is of course also safe, but the problem is that it doesn't reflect reality. The simulated world doesn't reflect the real world. So if you think a robot and there are engines and there is physics and there is friction, and if the simulation is not fully telling you how the world looks like, then the learning process might be very, very good on the simulation, but doesn't really work in the real world. And this is a big issue that prevented using simulation for learning for a long time. The Sim2Real Revolution is a set of techniques in which you learn in the simulated world, and you apply what you learned in the simulated world in the real world, and it actually works, okay? And this is something that theoretically could have happened a while ago, but it didn't. And with not a lot of novelty in terms of techniques, basically making the simulation a bit better and adding some noise in a sophisticated way to the simulation. But this was enough with the techniques of reinforcement learning, the modern techniques of reinforcement learning, and the large scale and the quality of simulation to achieve tasks that in the past took many, many years to accomplish. One example is a company that I founded together with Professor Lior Wolf from Tel Aviv University and Amnon Shashua. And it is called NT Robotics, and we built a robot and we trained it fully in a simulated world, and we apply the results on the real world, and the robot is just walking in the real world. So things that took companies like Boston Dynamics to do 10 years, now we can do in a simulation and apply it to the real world very, very fast. Okay, so this is a Sim2Real Revolution. Okay, and the last one is reasoning. So arguably reasoning is a holy grail of AI. Okay, we want a machine to reason, to be smarter than just memorize or know how to generalize for the same distribution. So to explain the difference, in classical machine learning, the type of results that we have is we get generalization on unseen data. So we do learn from one data and we generalize to unseen data. But usually we require that the training and testing data are IID from the same distribution. So they are identically, independently distributed from exactly the same distribution. So taking, for example, the task of detecting cars in an image, you collect a lot of data from the same distributions that you want to apply in your model. You label it, you learn a machine learning or deep learning model, then you apply it on the exact same distribution, and it works. This is classical machine learning. Reasoning is out of distribution generalization. So basically, you learn on one distribution, and then you give the model instruction plus few examples, and you get out of distribution generalization. So we see, it's something that we see only in the last year or so, that suddenly large language models, LLMs, we see reasoning emerges from these models. And it is very, very interesting to understand, to figure out why we suddenly see reasoning emerging from these models. They were not trained to reason at all. They were trained just to predict the next word in a sequence of words in the internet. So what happened? And at least our best guess so far is that the key is training on code. So maybe it's by luck, maybe it is by design, but for some reason we started to train large language models on a lot of coding tasks. Just taking from GitHub and from open source sources of code, a lot of code, and training the models to also to work on code. And this training on code gives them reasoning capabilities. So how it looks like. The first approach, very, very old one from 2022, is called chain of thoughts prompting. And it works something like that. So in standard prompting, you show one example. This is one shot. Okay, so you show the model in the input, in the prompt. You show him a question. So here Sean has 5 toys. For Christmas he got 2 toys, each from his mom and dad. How many toys does he have now? And you tell the model that the answer is 9. And then maybe you give more examples, and then you give the last question, okay, and answer, and then the model needs to predict the outcome. And it often predicts a wrong outcome, okay? No reasoning. Chain of thoughts prompting is a variant of it in which you don't only show the final answer, the answer is 9, but you explain the model how to think about the problem. So you tell him, Sean started with 5 toys. If he got 2 toys each from his mom and dad, then that is 4 more toys. 5 plus 4 equals 9, so the answer is 9. And once you do this, then suddenly the model is able to follow the chain of thought thinking and do some reasoning and come up with a right answer. So this was 2022. And then 2023, January 2023, there was a paper called PAL about program-aided language models, which did something similar, but it actually showed the model how to translate the question into Python code. Okay? And so if we look at some question, Roger has 5 tennis balls, he buys 2 more cans of tennis ball, each can has 3 tennis balls, how many tennis balls does he have now? So you tell the model, Roger started with 5 tennis balls, so let's write it as tennis balls equals 5. It's a Python, 1 line of Python. Then 2 cans of 3 tennis balls each is, then define a variable, both balls equals 2 times 3. You don't even have to solve it, just define this variable. And then the answer equals tennis balls plus both balls. Okay? And then even when you go to a pretty complicated mathematical question, by breaking it into code, the model is able to follow the instruction, translate them to code, and then give the right answer. And you see here there is a pretty complicated equation for, thinking about only in the head is complicated, but once you write it down, especially as Python code, then it makes it much easier. By the way, it means something about our education system. Maybe we should also teach children in elementary school to code. because it helps with reasoning. Of course, we want students to know to code. Okay, but what is the next step? The next step is something that we call neuro-symbolic reasoning. So statistical learning is learning from examples. You show examples, and it is called induction. You want from the examples, from the specific to the general rule, okay? Symbolic learning is usually the other way around. You learn from rules. It is deduction, okay? So you tell the model the rule. So there are things like learning to multiply any two numbers, okay? If you try to do it using example, it doesn't make sense, okay? You don't want to show a lot of 5,342 times 2,175 equals to something. I don't even know what's the answer, okay? Instead, you want to teach the model the multiplication algorithm, okay? And then it just needs to know how to translate the problem into the algorithm and execute the algorithm, okay? So in neuro-symbolic approach, the idea is that you come up to a problem, you want to translate the problem into Python code snippets, execute them, and translate the Python output to an answer. Okay, and then you can enjoy both worlds. So we wrote at AI21 a paper about how to achieve a neuro-symbolic architecture, and so we did it in May 22, and many time after that, Meta, Facebook did something similar. It was actually last month. So here are some examples how it works. So you have you have the ability to call some functions in Python that helps the model to figure out things. Like, let's look at the second example. Out of 1,400 participants, 400, and then the model itself say, or calculator 400 divided by 1,400 equals 0.29, and then it makes this answer 29%, pass the test, okay? Or you can have another symbolic or some microservice, like the Brown Act is California's law, and now I have no idea what is a Brown Act, so I just open Wikisearch Brown Act, takes the first sentence, and then it helps the model, tells you that requires legislative bodies like city councils to hold their meetings open to the public. So by combining the ability of communicating with natural language and calling symbolic engines like Python, like search, like specific engine, we get the neuro-symbolic reasoning, and then we give AI a very capable, a very strong capabilities in reasoning. Okay, so this was a long introduction. How much time do I have? 10 minutes. Okay, so okay, very short time. So where are we going from here? So we see AI models that can learn in context and reason and operate in the real world, like Sim2Real. This will create a new era of machines or robots that can be instructed by humans to perform various new tasks with out-of-distribution generalization. Okay? And you see that the pace is amazing. And the immediate question is, should we be alarmed? Okay? 4 years, 4 revolutions, 20 years, 6 revolutions. Where are we going from here? Is AI dangerous? And if so, why aren't we scared? So since I don't have a lot of time, I will focus only on the second thing. I wanted to show you first how we tackle the problem of safety of AI in self-driving cars, because self-driving cars is an example of a very, very sophisticated piece of technology which requires a safety level which is really, really high, okay? It cannot make mistakes, basically. So how we handled it. And we had some unique way to do it in Mobileye, but I don't have time to talk about it. So the question is, what about general AI? And can we learn something from what we did in Mobileye for self-driving cars to the general AI alignment problem? So I will skip the part about Mobileye, and you are missing all the fun videos. Maybe I will just give the one slide of the approach. So our methodology for safety is falling into a safety paradigm which is called assume guarantee. And the idea is to define a small set of reasonable assumptions on how other agents, people driving cars and pedestrians, behave on the road. And then we have a very strong AI engine, but we put on top of it a safety net, something that we can prove mathematically that it must be safe and must guarantee certain type of rules. And there is a lot of work how to make it, this logic model, complete and sound. So we tackle these problems, but at the end of the day is a safety net that guarantees that although we have many machine learning components that you can't always know exactly what they will do in any situation, you have a safety net that guarantees that you will be fine, okay? And okay, so for self-driving cars, we have a safety net with mathematical guarantees. And the question is, can we learn something from it for the general AI alignment problem? So what is an AI alignment problem? The best way to tell this story is using Mickey Mouse from Fantasy 2000, from the story of you want to fill a cauldron, okay? And you have suppose that you have a reward function. The AI gets 1 if the cauldron is full and 0 otherwise, okay? Now, what is a modern AI building? Modern AI building translates to optimizing a reward function, okay? It translates into solving an optimization problem and optimizing it. Suppose that we can optimize it very, very good. So the reward function that we defined might end up with a flood, okay? Why? Because even though the reward looks same, okay, 1 for a full cauldron, 0 otherwise, it is not aligned with what we really want. What's the problem? The problem is that if the cauldron is 99.99% full, we are fine with it, but for this reward function, the AI will not get the 1 reward in this case because we said full, okay? So the AI can translate what we ask for as we really want a full cauldron. Now, evaporation of water a little bit might make the cauldron be only 99.99 full. So to make sure that it will always full, it will keep bringing more and more water into the cauldron, and we end up with a flood because we didn't have anywhere in the objective that we don't want a flood, okay? So how can we solve this problem? Maybe the approach for self-driving cars, some safety net, a stop button maybe for the AI. So the problem is that a stop button is an obstacle to the AI reward. So if it is super intelligent, it might stop you from pressing the stop button. Okay, so maybe let's add a reward if the stop button is being pressed. But this is also not good because then the AI will press it itself. So let's not allow the AI to push it, but it's also not good because the AI will manipulate you to push the button. So the bottom line is, if you are dealing with someone which is really smarter than you, then there is no way to go around it. Stop button will not work. So are you scared? So most AI researchers are not scared. Why? Maybe researchers believe that the problem is only for artificial general intelligence, which is super intelligent, much more intelligent than us, and we are not there today. So I gave here an example how you can see something like that with today's technology, and I chose self-driving cars. So suppose we have a reward for safety, a cost for accidents, for comfort. We want the drive to be very smooth. And for usefulness, we want to maximize the speed up to the legal limit of the cars. Sounds good? All right. Now all the cars will suddenly stop. People will get confused, will go out of the cars, then the cars will lock themselves and start driving at a constant speed on the highway. Okay? What we forgot to embed in the reward is that we want people to actually use the service. Okay? So no catastrophic result here, but people will lose trust in, lose confidence in the service, and it actually might hurt us. So we want to solve this AI alignment problem, and it is a problem even with today's technology. So now, are you scared? So in a sense, if you think about it, almost all of science and technology advancements are dangerous in retrospect. And when Einstein studied the relationship between mass and energy, at the end of the day, it led to an atomic bomb. Or inventing the combustion engine had a big effect on climate change. So is AI really different than the rest of technology? So we think it does. Okay? And we distinguish between strategic AI alignment problem and agnostic alignment problem. Strategic AI alignment problem is that when the AI tries to change deliberately the distribution in order to optimize a reward. Agnostic alignment problem is AI optimizes a reward, and there is a butterfly effect that sometimes later leads to a catastrophic event. Okay? And the second one, agnostic alignment problem, is shared with all of science and technology, and in a sense is not solvable without stopping progress. But strategic alignment problem is unique to AI. So, and we show in the paper that we can, and I think we should, prevent strategic AI alignment. We prove that learning from data is safe, but learning from experience, when you give the machine the ability to get improved with the experience, then it can suffer from strategic AI alignment, but you can eliminate it by working with a buffered environment and a human validator. So you want to, whenever you want a machine to learn from experience, you want it to be in a simulated environment, and you want some human to supervise the process. And we show that this can prevent strategic misalignment if we don't suffer from the matrix problem. What is a matrix problem? It's not something in mathematics. It's Neo from the Matrix movie. So we might think all is good, but it's not, and I will stop here. Thank you.
Well, thanks again for a really great lecture. So you show this idea of calling external APIs, and everyone is wondering about the next advances about reasoning. And I wonder what your thoughts are about the ability of model to actually create these representations of rules rather than just call them external.
Yeah, great question. So in a sense, they are already doing it today because the models today know to write code. Okay, they know to write functions. So today it is still somewhat limited because they're not, writing a whole code base. They're writing dedicated functions. But I'm pretty sure it's going to be in a place where an AI can have its own code base and get improved and improved over time and really have amount of code that we humans will not be even able to follow. So it's going there.
Well, think that, in my mind, the major problem is that we really do not understand how it works. We just experiment with that. Do you have anything, maybe if we will understand, we will be less worried and know how to handle it. So how do you see this problem? How do you see the advancement in this problem? Understanding why those huge models, this architecture, etc., that thing indeed work, not just experimenting with this.
Well, I'm not sure that I share that this idea that if we will understand how it works, we will not have to worry. In a sense, we do understand much better.
What to worry about.
Yeah, but I mean, even this, I'm not sure I share this this rationale, because take artificial neurons. At the level of an individual artificial neuron, we understand perfectly how it works. Unlike biological neuron, which even in the single neuron, we don't really understand everything how it works, okay? We understand the artificial intelligence much better than what we understand human intelligence. The problem is that complexity comes with scale, okay? So even if we understand the components, we don't understand. You can have a very, very complex system out of components which you perfectly understand each individual component. The complexity comes from the combination of the individual things that you perfectly understand. Now, understanding it will not give you any comfort, because still you can build something very, very complicated. Even think about coding. We understand perfectly how coding works, right? We understand it fully. Does it mean that you can understand every software piece? No, you can't understand if it is too big, okay? So I can take code in Python, okay? Just it's too big for one human to go over it, then you will not understand how it works. It's simply too large for our mind. And I think this is what's happening with these big models. We do understand the component. The scale kills us in terms of understandability. Maybe Mike, yeah.
Hi there. I'd like to ask a question about the AI alignment problem. Basically, you were saying that it will be solved by maybe using a safe environment, having a human validator. That is a very good idea in general, but how it's not very industry applicable. Are you suggesting that the solution to the AI alignment problem would be through policy? Is there no algorithmic approach? Is maybe like a future TensorFlow library for AI alignment, something in that direction? What do you think will solve this?
I think, well, first, to be honest, I'm not optimistic about solving it, because it involves regulation, and it involves agreement between all the world, and we know how the world works, and it's very difficult to have agreement of all the world. So it's mainly, the solution is not a TensorFlow library, it's conceptual. You want discipline. And the discipline comes from, don't just throw the AI out there and let your user use it endlessly while it keeps improving itself in the wild, because this is not safe. Instead, you want to control it in some way. And one good way is, it's fine to have a version out there, okay, collect data, now simulate, okay, not out there, but in a controlled environment, in a buffered environment, validate that the results is indeed aligned to the best of your ability to validate alignment in the buffered environment, and release a new version. Now, a lot of, many companies apply this approach, not only because of AI alignment, but because it is scary for a company to put some agent out there and let it, learn, and it can convert to misbehave, and it will impact the company. But I think that with the advancement that we are seeing, There might be some companies that will decide maybe it's a good idea, and part of what I'm trying to argue is that it's not that good. It's not such a good idea.
Can you please comment on the state and future of self-driving cars? Because as a non-expert citizen, there's very confusing information in the press. It seems that the Sim2Real problem is far from being solved there.
Okay, so today I arrived here with a self-driving car from Jerusalem to Tel Aviv that drove all the way door to door until the parking of the museum here. So just to give a glimpse of the state. Now, it doesn't mean that we are ready for letting the driver go to sleep or not be in the car at all. I was still supervising the car because it is a car that was intended to be what we call a eyes-on system or level 2 system. It still requires the supervision of a human. The question of where are we going as an industry from here, then there are two directions that happen in parallel. One direction is what is called the robotaxi direction. These are level 4 systems, no driver in the car at all, limited geography, so what is called gated area. Okay, so you take a gated area and you put them service of robotaxis. This already works in the world. Waymo, Cruise have such services in the United States. So this is one direction. The problem with this direction is cost and scalability. The second approach, which is more aligned with the main business of Mobileye, for example, is to solve the scalability problem, so build a scalable solution that can drive everywhere, and gradually enlarge the level of autonomy. So, for example, in the coming 2 years, we will have something like what I experienced today, but the driver, it will be a consumer car that you can buy. The driver will be able to go to sleep or to work, to see a movie, but he will need to be in the car, and the car will drive itself only in certain types of roads, say only in highways. So if I'm coming from Jerusalem to Tel Aviv, then I drive 1 kilometer until I go into the highway, then I'm driving autonomously, can go to sleep, can do whatever I want until Rokach, and then in Rokach I again need to supervise the car until it gets here. And this will be consumer cars, okay? So everybody will be able to buy it, meaning that we believe that we solved the scalability issue, at least in some domains. Now, as you take the system to more and more challenging environment, it will be more gradual progress. And then gradually, you will be able to enjoy this car in larger and larger, what we call ODDs, operational design domains.
Thank you very much.
One question?
Yeah.
What do you think about intellectual property when you train such big systems? For example, for visual data, for text that people write, poetry.
I'm not an expert in this, I don't know.
Okay, one final question. You talked about this gap between learning from observation and from action, that like learning from action is more dangerous. Presumably, if you have a lot of data, why can't you build a causal model of the machine? The model can build a causal model, and then there's no need for action. Why intuitively is there a gap?
So what you are saying is learn a causal model of how the evolution of the world works, and then what? And then optimize on this model and not on real data.
Yeah. So I mean
this is perfect. This will be safe. This will be safe. This is like learning from data because at the end of the day, this is a distinguish between an offline process, validation process, and then online process that uses it. So whenever you have a validation phase between the training phase and the application or releasing the model out there, if you have in the middle a validation phase, you are fine. The problem is when you want that the model will be released and will keep improving while it is in communication with the world. Then it can suffer from strategically misalignment.
Okay, thanks again for a great talk.
Thank you.